So this is part 2 of the chapter 2 lecture. And we had just been talking, we were just talking about covalent bonds. And a covalent bond is when two atoms are sharing electrons in order to each feel like they have more electrons than what they really do have. So the term electronegativity refers to an atom's affinity for electrons. Affinity means attraction or desire for electrons. And all atoms do desire electrons, but there's differences in how much they desire them. So we said that our 4 most important atoms, we said were carbon, let me get my pen, carbon, hydrogen, oxygen, and nitrogen. So what if I tell you that oxygen and nitrogen are very electronegative? They really want electrons. I'm just going to put very, En. And carbon and hydrogen are not so much, not as much electronegative. I mean, they, Okay, so that looks terrible. Okay, so oxygen and nitrogen are strongly electronegative. Carbon and hydrogen, not so much. If you can remember that, and I would memorize that, then you would be able to figure out what bonds between two atoms would likely result in what we call equal sharing of electrons between the two atoms or unequal sharing of electrons between the two atoms. And remember, sharing of electrons is a bond, so what we're really saying is what covalent bond would result in what we call a nonpolar bond, and what covalent bond would be what we call polar. Now, like I said, carbon and hydrogen are similar to each other in that they're not that electronegative. Oxygen and nitrogen are similar to each other in that they're very electronegative. So if you have a carbon in a bond with a hydrogen, neither of them is really more electronegative than the other, so they're going to share the electrons in the bond very equally. All right, they're each pulling on the electrons a little bit, but not one more than the other. So you can think of the electronegativity as how hard the atom will pull the electrons in the bond toward itself. So carbon and hydrogen, that bond would not be, it would be an equal sharing of electrons. And so that bond would be called nonpolar. Nonpolar. All right. Or a bond between oxygen and nitrogen. Even though both of them are very electronegative, they're both pulling really hard. Neither one is going to win. And so that bond would be nonpolar, surprisingly. Because even though they're both pulling hard, neither is going to win. Neither is going to be able to pull the electrons closer to itself. It's almost like a game of tug of war, isn't it? But if we take either carbon and hydrogen, so let's just do carbon, and make it in a bond with oxygen, the carbon is not pulling that hard on the electrons, but the oxygen is. So what will happen is the electrons will be pulled more in this direction. And that's what we call an unequal sharing of electrons. And so this would be a polar bond here. So carbon to oxygen, carbon to nitrogen, that would also be a polar bond. Hydrogen to oxygen, or hydrogen to nitrogen. These would all be polar bonds in the middle here, because you have one atom that's not very electronegative trying to share electrons with an atom that is very electronegative. And so like a game of tug of war, the electronegative atom is going to pull the electrons more toward itself, and that's considered unequal sharing. And what that does, so we're going to focus on these ones in the middle here. What that does is it creates, if you look at this first picture here, it creates what we call partial charges. And we're using the Greek letter, the lowercase Greek letter delta, which looks like an S that you kept going and then you crossed over itself again, sort of. So this little symbol here is the Greek letter delta, and it refers to the partial charge. The oxygen is pulling the electrons more toward itself, and remember, electrons are negative, so that side of the molecule ends up getting a little bit more of a negative charge. It's not a full charge, it's not an ion, but it's just a more negative at any moment. At any given moment, there's more electrons on this side of the molecule. And that means that the hydrogen has not enough electrons at most of the time. And so it ends up with a partial positive charge. Now, across the whole molecule, those cancel out. But if we're zooming in and looking at these regions within the molecule, the hydrogen side has a partial positive, the oxygen side has a partial negative. So that bond is called polar, and is really, if you think about the poles of the Earth, here's the Earth, here's the axis of the Earth. You have the North Pole and the South Pole. I don't know if you know this, but magnetically they're opposite. I can't remember which one is positive and which one is negative, but the poles are opposite. That's why a compass will always turn to one direction. But polar just means opposite ends. And in this case, it means a partial negative area on one end and a partial positive area on the other end. So that's kind of where that term comes from, polar, like polar opposites. And so when you have a polar covalent bond, that just means you have these partial charges. Okay? And partial charges really behave pretty similar to full charges. In other words, there's something of a negative charge on one side, something of a positive charge on the other side. Now, in an example, this polar covalent bond is between oxygen and hydrogen. So if we look at a whole molecule, which would be water, water has a polar covalent bond here and a polar covalent bond here, and the shape of the molecule is like this. And this is one you should just memorize because we're going to talk about water a lot. So we're not going to worry about every molecule in the world, but this one you need to know. So it actually is shaped like this V. In 3 dimensions, it's really shaped that way. And you'll notice that on the back, I guess what you could call the back end of the molecule, they're showing you some electrons, and then some of the extra shared electrons tend to kind of hover on this side. And so this is the partial negative end of the molecule, and then on the 2 parts of the V, I guess the 2 little sticks, those are partial positives because that's where those hydrogens are. All right. So water is shaped like this. So we say it's a polar molecule. All right. Other molecules, remember we said carbon and hydrogen are both kind of they're similar in their electronegativity. Neither is going to pull any harder than the other on the electrons. So those bonds are nonpolar. There isn't a partial charge on one side and a different partial charge on the other side because the electrons are moving equally across both atoms. So no partial charges when there's a nonpolar bond. And so molecules that have nonpolar bonds are called nonpolar molecules. And we're not going to worry about carbon dioxide right now. It's a special case. Let's not worry about that one right now. Let's think about water and then maybe some other things. But I really want you to focus on water right now. So water has polar covalent bonds, and it means the molecule has these regions of partial positive charges and partial negative charges. Anything else like methane that is made up of all nonpolar covalent bonds is a nonpolar molecule. And that differential, the difference between polar molecules and nonpolar molecules, is huge in the way that the molecules will interact. Because remember, we're thinking about the hierarchy. The molecules are going to interact to make macromolecules and eventually organelles. So this is important in how the molecules are going to interact with each other. So polar molecules contain these polar covalent bonds, and they have these regions of partial positive and partial negative charges. Nonpolar molecules are made with nonpolar covalent bonds. And so polar molecules and nonpolar molecules behave very differently from each other and pretty predictably in the cell. Okay? So we just said water is a polar molecule. It's shaped like a V. And then we put the partial positives on the hydrogens. And then we can put the partial negatives. Sometimes people put two partial negatives over here. It doesn't really matter. All right, so this back end of the water, I guess you could call it, is the partial negative end. It's always on the oxygen side. And the partial positives are always on the hydrogen side. So, you know, once you get used to that, it's just automatic. All right? And that's because the oxygen is pulling the electrons more towards itself in both bonds. And so it's kind of hogging the electrons most of the time. All right? So that's water. Water is critical in biology. And the way water behaves has everything to do with the fact that the molecule has these partial charges. All right. Now, hydrogen bonds. I think I told you earlier that hydrogen bonds are bonds that form between two or more separate molecules. So we're not talking about the bond within one molecule. Those are called covalent bonds. So a water molecule has hydrogen, hydrogen, oxygen, and those are connected by covalent bonds, right? But the hydrogen bond, you know, they didn't ask me. I think this is a terrible name. I wouldn't have called it hydrogen bond, because the hydrogen bond is not the bond, like a hydrogen bond is not, write this down, a bond between two hydrogens. Even though I'm putting quotes here. A hydrogen bond is not a bond between two hydrogen atoms. Not a bond between two hydrogen atoms. That's not a hydrogen bond. That's a covalent bond. I can't even write with this mouse. The definition of hydrogen bond is the bond between, all right, the partial positive side of one molecule, which is always near to the hydrogen, and the partial negative of another molecule. So let me show you how I'm doing this. Let me see if I can draw this a little bit better. Let me erase this here. Erase, all right. So one water here. This has the partial positive. And then another water, I'm going to orient this other water on purpose this way. Yeah, it's not any better, is it? But do you see how the oxygen, the back end of the oxygen, which is the partial negative side, is facing the partial positive of a different molecule? So the attraction between the partial positive and the partial negative charge is almost like an ionic bond, isn't it? Those opposite charges are going to attract. But it's weaker than an ionic bond. So it's only a partial positive and a partial negative. It's not a full positive and a full negative, so it's kind of a weak bond. And we draw it with a dot, dot, dot. The back end of one water molecule, the partial negative end of one water molecule, has a weak bond with the partial positive side of another water molecule. And then this one over here, this partial positive and this one each could make bonds with other water molecules. So here you just keep extending it. So this would be a dot, dot, dot right here. And then this one could make a bond to another water. And this one, so all of these, you can have a lot of hydrogen bonds happening between all these different water molecules. And in liquid form, water is always moving. So each molecule is always moving. So molecules are moving around each other. So the bonds, the individual hydrogen bonds are breaking and reforming in all different ways, but at any one moment, at any one snapshot of time, you have a large number of hydrogen bonds in place. And that makes water hold together as a liquid. So what we typically say of hydrogen bonds is individually, any one of these hydrogen bonds is very weak. But because you have so many of them in water, collectively it holds, it's strong. So individually weak, but collectively strong. And these hydrogen bonds, which are the result of water having partial positive and partial negative charges, these hydrogen bonds are what makes water so special. Why, when we look for life on other planets, what we really look for is evidence of water, or the evidence that water has ever been there. Because water is so fundamental to our understanding of how life works that we can't even, we hardly can imagine life without it. It may be a blind spot for us scientifically, because I think, there could be some form of life that doesn't rely on water, but we tend to look for water because we almost can't even imagine any other option. All right. Okay, I don't want that. What am I trying to do? Okay, so what are these special properties of water? The thing about studying water is you're so used to it that it doesn't seem special. And only if you studied other liquids, then you would see how unusual water actually is. So I don't know if I'm going to be able to convince you that water is really cool and interesting and special, but in fact it is. Water has a very high, what we call specific heat. Specific heat is defined as how much energy it takes to increase the temperature. So if you ever watched a pan of water boil, here's an experiment. Don't try this at home. Get a pan of water and a pan of alcohol, pure alcohol. Again, don't do this at home. It could start a fire. But if you did that and you were safe, and you used the same volume of liquid in each, same volume of water in this pan and the same equal volume of alcohol in the other, the alcohol would boil almost instantly when you turned on the burner. And you guys know how long it takes water to boil. It's like forever. You're sitting there staring at it and it's not doing anything. So it takes a huge amount of heat to make water change temperature. We're just used to it. But alcohol almost immediately will boil. Again, don't try it. You might start a fire. Water has a high heat of vaporization. In the same way, it takes a lot of heat to make it turn into a gas. A high amount of heat to make it boil, a high amount of heat to make it become a gas. I mean, everything about it takes a lot of heat. All right. So water is special in that way. So what that means is that the temperature of water remains stable even when the external environment temperature has changed quickly. So air changes temperature quickly, but water changes temperature slowly. Have you ever jumped in your pool? If you have a pool, have you ever jumped in a pool, the first really hot day of summer and the pool is still ice cold from the winter because it takes a long time for the temperature to get up. And then in the winter, when the air temperature drops quickly, the pool is still warm. And it takes a long time for the pool to cool down. So the water really is very slow to change temperature. That's important because it helps aquatic animals not have this immediate change in temperature, which would probably kill them really quickly. Now, another interesting thing is that ice floats, or in scientific language, we say solid water, which is ice, is less dense than liquid water. That means it floats. All right, that's really unusual because usually the more solid something becomes, the more packed together the atoms become and the molecules, and the heavier and more dense it is. But water is different because when water freezes, when the molecules of water are moving around each other, they bump into each other. But when water freezes, they actually spread apart from each other and hold each other at I guess you could call it an arm's distance if you think about the two bonds in water as being almost like arms. So when water freezes, it expands outward, which is odd. Most liquids don't do that usually, but if you've ever put a water bottle, filled it all the way to the top, screwed on a cap, and put it in the freezer, it'll break your water bottle every time because the water expands as it freezes. That's unusual. Other liquids don't do that. Water is a good solvent, and we call water the solvent of life because we can't imagine, like I said, water is the main solvent in the cell. It's the main component of the cell, the liquid part of the cell. And so water is the solvent of biology. It's the thing that everything is dissolved in, all right? So whenever we talk about a solvent in this course, it's always going to be water because there is no other solvent that's important for life. Now, if you go into chemistry, there's other solvents, but they're not, you know, life doesn't depend on any other solvents. Water is the solvent of biology. Now, when you have water, water is a polar molecule, right? And so we have a rule in science, we have a rule in chemistry, and we say like dissolves like, which sounds like I'm just talking crazy. Like dissolves like. So what that means is water dissolves things that are like water. And what we mean by that is water is polar and partially charged. Things that are either polar or partially charged or fully charged will dissolve in water. So things that mix with water will be things that are polar, which means partial positive and negative charges, or things that are ions, full positive and full negative charges. Those things mix well with water. So polar molecules will dissolve and ions will dissolve. Now, what will not dissolve in water? Nonpolar. Nonpolar things are not like water. And so nonpolar things will not dissolve in water. So anything that dissolves in water or mixes well with water, we call hydrophilic. So polar molecules are hydrophilic, ions and salts are hydrophilic. Things that are hydrophobic are nonpolar. Things that, and guess what fats are? Fats are nonpolar. And oil. And you guys know oil and water don't mix. That's because oil is hydrophobic. All right? Oil is made mostly of carbon and hydrogen bonds. Carbon and hydrogen. All right? So things dissolve in water and that are hydrophilic, which means polar or fully charged. Things that don't dissolve in water, things that don't mix with water, are hydrophobic, the fear of water, so to speak, and that would be things that are nonpolar, which would include fats and oils. And that makes sense because you've tried to mix oil and water and they don't mix. Now, water has properties that, now number 5 has to do with hydrogen bonding. We say that water is both adhesive and cohesive. Adhesive means it sticks to other things. Cohesive means it sticks to itself. And the cohesive properties of water is the hydrogen bonding that holds the atoms together. Cohesive. Adhesive, water likes to stick to other things like glass or little, you know, there are certain things that water will stick to pretty well. So water has certain adhesive and cohesive properties. And it really has a lot to do with water will stick to things that are hydrophobic and not to things that are, water will stick to things that are hydrophilic and not stick to things that are hydrophobic. But we'll talk about this on the next slide, what adhesive and cohesive, why that matters. And then interestingly, water can break apart. Molecule of water can break apart. Small amounts of water molecules will break apart. And when water breaks apart, it forms an ion called the hydroxide ion and the hydrogen ion. So this would be a water molecule that has broken apart. The hydroxide ion and the hydrogen ion. All right. So let's go back to that number 5, cohesive and adhesive. Cohesive and adhesive properties means that the surface of water holds together with enough firmness that small, very small insects can actually walk on the water. And you can see the legs of this insect kind of pushing down on the surface, but not breaking the surface. Isn't that interesting? Now, if the weight of the animal gets much more, then it will fall through. But that's because the surface of the water is cohesive with itself. The water molecules are holding to each other really quite strong. And if you put a teeny tiny glass straw, which we call a capillary tube, into water, the water will move up. And why? It's because the water is attracted to the glass in the tube, and water is attracted to itself. So cohesive and adhesive, and the water will just sort of crawl upwards against gravity. And that's an artificial situation where you put a glass tube in a beaker of water. But the equivalent of this would be roots from a plant that go down into the soil, and the water can go up these very thin tubes in a plant, and they can move up against gravity. So both of those are called, that's called capillary action. The tendency of water to move up a very narrow tube against the force of gravity. It's called capillary action. So how does something dissolve in water? The way something dissolves in water is the water molecules will surround the item. And in this example, we have two ions. This is the chloride ion, and this is the sodium ion. So if you mix salt and water, the ionic bond between the sodium and the chloride will break, and each ion will be surrounded by water. Now the chloride ion has a negative charge, so do you notice which part of the water molecules are facing the chloride ion? Isn't it the partial positive ends of the water molecules that are attracted to the negative chloride ion? And they've only shown 3 water molecules here, but you can imagine like a lot more than that. All right? And so it creates this whole bunch of water that's surrounding this ion. And we call that a sphere of hydration surrounding that chloride ion. Over here, the water molecules are also surrounding the sodium ion, but it's the partial negative of the oxygen side of the water that's facing towards the positive charge of the sodium, but you will still get this sphere of hydration. And so by water creating these a layer of water is forming around each of these ions, that's how something becomes dissolved in water. That's really the definition of being dissolved in water, is having a sphere of hydration that will naturally form around that item. And that's why water will dissolve anything that's partially charged or fully charged. If it doesn't have a charge, if it's nonpolar, then you won't get a sphere of hydration around it, and it can't mix with the water. All right, now what about that other issue about the water molecules breaking apart? Water molecules will break apart, and looks like I've got a little error issue here. Okay, I couldn't read all the writing. Water molecules will break apart, and when the water molecules break apart, you will get a little bit of hydroxide ion and a little bit of hydrogen ion. All right. Now, the amount of hydrogen ion in in water is measured by a scale we call the pH scale. So plain water will have an amount of hydrogen ion in it naturally that corresponds to pH of 7. And what pH of 7 actually means is the concentration of hydrogen ions is 10 to the negative 7 molar. Molar is a concentration measurement. but we just, instead of saying 10 to the negative 7, we just focus on that 7, okay? So water has a pH of 7. If you add more hydrogen ions to that water somehow, then the concentration of hydrogen ions increases, but the pH number decreases. All right, so pH 7 is, you can think of that as your starting point for neutral. Any plain old water has a pH of 7. If somehow you add just more hydrogen ions to that water, you will cause the pH number to go down, so 6, 5, 4, 3, 2, 1. But that means that the hydrogen ion concentration is higher. Adding more hydrogen ions lowers the pH, and the liquid becomes more acid. All right? But each of these numbers, 7, 6, 5, 4, 3, 2, 1, each of these is actually, like I said, it's really 10 to the negative 7, 10 to the negative 6, 10 to the negative 5, 10 to the negative 4. And so it's actually a power of 10 difference between these. So it's what we call a logarithmic scale. So the difference between distilled water and urine in terms of the acidity is not 1. Urine is not 1 time more acidic than distilled water. Urine is 10 to the 1 times more acidic than water. Black coffee is not 2 times more acidic than water. It's 10 to the 2 times more acidic, so 100 times more. So what you do is, with these numbers, if you're comparing two liquids, and you're saying which one's more acidic than the other, the more acidic one is the one with the smaller number. And you take the difference between the numbers, and that becomes the power of 10. So 7 for distilled water, 5 for coffee. So the difference between that is 2. So black coffee is 10 to the 2 power times more acidic than water. All right. Now, any pH above 7, we call that a base. All right, so basic substances cause the hydrogen concentration to become lower, and it causes the pH number to increase. But this is a logarithmic scale, a base 10 scale, and so you want to keep that in mind. So seawater is not as acidic as distilled water, and it's not 1 time less acidic, it's 10 to the 1 time less acidic. All right. So that's, you have to think of it in a base 10 fashion. All right, buffers. Buffers are solutions that can bind to hydrogen ions or release hydrogen ions depending on what's needed in order to keep the pH of the liquid pretty steady. The most common buffer in biology is bicarbonate. Bicarbonate is H2CO3. Bicarbonate ion is HCO3 negative. But bicarbonate is, if you've ever heard of bicarbonate of soda, it's baking soda. Baking soda is something that actually exists in your blood in nature. It's actually part of your body, which is weird because it also comes in a little orange box. But bicarbonate is a natural buffer in your blood. And so if you eat things that are too acidic or too basic, it keeps your blood from having a quick shift in pH, because that could kill you. So it's important that you have this bicarbonate in your body. You don't need to memorize the equation, but the definition of what a buffer is helpful. All right, I'm going to take a break and we'll finish out the last part of this lecture.